Our learning objectives, which you will already have seen, are to focus on fenestration modeling software that can be used to predict energy savings as one aspect of bioclimatic design. We'll talk about both fixed and operable systems. I will show you examples, uh, and that will include vegetated screens, which are quite popular in some parts of the world and could be more widely used. We'll also discuss some of the unique material selection considerations related to longevity and the specialized, unique corrosion environment that exists, as well as the structural design standards for stainless steel and some other commonly requested pieces of information. We'll start with the modeling software and some basic stainless steel information that you need. First of all, uh, bioclimatic design is an old concept. If you look at buildings built hundreds of years ago, they often took this into consideration to try to make the inside of the building thermally comfortable. With our technology, we've been able to add to that, and there's been an increased interest in building for the environment, sorry, to increase thermal comfort inside while minimizing energy use. An important part of that is sun shading, and that will be the primary focus of this presentation, although I will briefly touch on roofing, which is another area where you can help to reduce energy use in a building. So sun shading, whether we're talking about the traditional overhangs that you find on some older homes or newer designs, canopies, awnings, louvers, movable versus fixed shades, there's so many different options. In general, having shading on the outside of the building or window is far more effective than internal shading. It can reduce summer window and wall heat gain. So if we can reduce the amount of heat that comes into the building, then we're dramatically reducing the need for air conditioning. In hotter climates, shading walls, not just windows, can also be very effective in minimizing the amount of energy or heat that is transferred into the building.
I'm holding and drag and then releasing. Okay. All right, so the click pattern is a little different. It's probably.
And
Yeah, the
can
click
you hear
pattern is a little.
background noise?
Yeah, breathe.
Thank you. So some general considerations. Software modeling is available to help you calculate the expected energy savings. This can be shading, can be valuable as in addition to new construction. I think it would be rather difficult to reach USGBC LEED Platinum without some level of shading on the outside of a building. For existing buildings, it can be part of modernizing the appearance and either reducing energy use or potentially avoiding the use of air conditioning. So there are several types of sunscreen designs, but they're generally split into active and passive. And I do apologize that the transcription is covering that up. This is an existing engineering building in Italy where, as part of the renovation, they added perforated stainless steel sunscreens to the south-facing side of the building as one of the changes that were made, in addition to insulation, to decrease energy costs and make it more comfortable for occupants. There are a variety of things that have to be considered as you look at facade and shading performance. It's not just about energy savings. It's also about aesthetics and security, um, durability, weatherproofing, aesthetics, the comfort and health of the occupants. So many factors, in addition to energy, are help to justify the use of sunshades. There are many tools out on the market. I am specifically in pointing you towards some that are free. And these are free tools that were developed by the U.S. Department of Energy at Lawrence Berkeley National Lab. But I should note that Lawrence Berkeley has partnered with China and Singapore and India, among others, who are doing their own testing and helping to contribute to the databases that help use the system. And so there are governments around the world that are using and building on this free software. So there are a number of pieces of software that you can obtain if you go to the Lawrence Berkeley website. Therm is one. It's a two-dimensional building heat transfer modeling system. So for any component where there might be thermal bridging concerns, you can use it to make an assessment. Comfen, which is going to be the primary focus of the presentation, is a means of modeling fenestration systems so that you can determine what is most efficient and compare different design and shading options. It is a very simple interface, but behind that is a very powerful piece of software that can give you a great deal of data to help guide your decisions. There are other pieces of software that are also available on the Lawrence Berkeley website on the same page. The CGBD is a database of different shading devices and materials and the testing that's been done on them so that you can use that information in your modeling. Window is for calculating window thermal performance and to help guide you into what is actually most cost effective, beneficial for your project. There are others. So I do encourage you to explore a bit, but I'm going to focus on Comfen, which, as I mentioned, is a very simple interface. I think that most people could sit down if you're involved in building design and use this without a great deal of effort because they have made it simple. I should note that Compton was built by first analyzing hundreds of buildings around the world of different types in different climates, different geometries and orientations. So it isn't just it's not based on assumptions. It's based on hard data around the world in different climates. It concentrates on the materials, the type of shading, interior versus exterior, and its relative benefit, window type, size, orientation, insulation, double pane versus not, weather variables, including the varying sun location and angle, different sides of the buildings, it pulls in energy inputs so that um, you can, uh, you know, if you're in a given region, you're pulling in representative energy information. So it's a wealth of information made simple. So what's the benefit? On a hot summer day, uh, you can potentially, on average, reduce your peak load by 25%. And by doing that, you're reducing the load on the grid. If we were to do this with all buildings, we would substantially reduce our energy requirements. Here's an example. And I did want to thank GKD for sharing this with me. This is deliberately a building in a relatively cool climate. It's in Michigan, which is one of the states in the United States that gets a lot of snow in the wintertime. And the daytime temperatures during the summer are not high compared to the warmer U.S. states or hotter locations around the world. So in this analysis, um, they looked at the building temperature with and without shading on the southern side. It was 34.4 centigrade for the building exterior without shading, and the shading dropped that temperature to 27.8. Um, and I should note, I've seen the comments about the subtitles. I don't have control over them, and they seem to be automated. So I apologize that the part of the slide's being cut off. So here we have 3 different facade variations. No metal fabric as a sunshade. This would be a passive sunshade without automation. 50% open area and 35% open area. You can put in a number of basic variables like this and then calculate the heating and cooling costs, and you can see that some of the the graphics that are provided in the analysis. But there is a substantial difference, and ultimately, with a 50% open area mesh, there's the potential of saving 24% on energy use, and with 35% open area, about 30%. So ultimately, it's a decision about how much visibility through that screen is needed if you have a fixed screen. But you can see that even in a cooler climate, this makes a substantial difference in your energy use. I wanted to review a few critical resources related to structural design and sustainability. So first, if you're using a stainless steel sunscreen, or it could be a sunscreen that's made out of wood or some other metal, you should consider using structural stainless steel to support it. I'll talk a bit later about why this is such a corrosive environment. It is also very visible to everyone inside the building. So in the last few years, we've had some wonderful new structural design resources that have been published. AISC 370 is the specification for structural stainless steel in buildings. AISC 313 is the code of standard practice for it. These are the sister documents to the carbon steel equivalents that you might be familiar with. The Code of Standard Practice relates to fabrication and erection. Those were both published in 2021, late in the year. We last month, the ASCE 8, after 20 years, was finally published. We have a 22 date on it because that's when the committee finished, but it was just published. So if you haven't seen it, you might want to get a copy if you work with cold form stainless steel. Additionally, the AISC Design Guide 27 was updated as part of this process. So there is a great deal of structural design information available in terms of design and specification with structural stainless steel, which we do hope that you will use to support your sunscreen. And here are the AISC publications. I did want to quickly review some basics as we talk about stainless steel. If you're used to working with other materials, uh, there sometimes can be some lack of communication because of terminology. From a stainless steel standpoint, grade means the chemical composition to those in the stainless steel industry. We do know that in other industries that could mean quality level, for example, or strength level. And but it is generally meant to mean alloy if we're talking to a stainless steel producer or service center. The stainless steels are grouped into alloy families based on their microstructures, and then they have different mechanical and physical properties that are unique. And then the corrosion resistance of each family is different in different service environments. So I'm only going to touch on those briefly, but I did want to make you aware that this is different from carbon steel or some of the other materials you might be familiar with because of these differences. Stainless steel gauges are not defined in any standard. So please specify the actual thickness, not the gauge. Select the stainless steel based on corrosion resistance first. Determine the level of corrosion resistance that you require. And then among the options that meet that requirement, hone in on the mechanical and physical properties that are preferred for your application. Um, Stainless steel specifications list the minimum required strength. It is possible in some instances to obtain higher strength levels because, you know, we do just list the minimums. So that is an option. There's only one ASTM standard A1069, which is for laser and laser hybrid welded stainless steel, where those different strength levels are mentioned as options. Otherwise, it's by negotiation with the producer. So the families of stainless steel that are typically used for all applications, but are specifically covered by these structural design specifications, are first the austenitics, like 304 and 316, which many of you will be familiar with. The austenitics can cover a broad range of corrosion resistance levels, with 304 and 316 being closer to the bottom end. Well, we have alloys that can be submerged in seawater and not corrode. They're strengthened by cold work. They're easy to weld, have high formability, and are not magnetic. Although, if you have a casting, you might have a slight magnetic pull without that being a problem. The duplex stainless steels are, I should mention that austenitic is the type of grain structure that you have with those steels. The duplex stainless steels have a mixture of austenite and ferrite in their grain structure. We metallurgists are very creative in our nomenclature, as you probably can tell. So the duplexes give you a wide range of corrosion resistance as well. They are much stronger, potentially double the strength of an austenitic stainless steel, although you can cold work austenitics. They are more resistant to chloride stress corrosion cracking and crevice corrosion, which I'm going to talk about briefly later in this presentation, because that can be rather important in this type of application. They include the precipitation hardening alloys, but specifically for tension bars and fasteners. I do want to note one big change in ASCE 8 is the addition of duplex stainless steels. So in my mini discussion about structural design, I wanted to show the strength differences between austenitic stainless steels, duplexes, grade 50 carbon steel, and a 6061 T6 aluminum for reference. You can see how much stronger the duplexes are. For some applications, like this sunscreen on the Novartis headquarters in Boston, Massachusetts, the strength of that 2205 was needed, as well as its corrosion resistance. So those plates and most of the plates, not all, and the bars behind holding up this sunscreen, this stone sunscreen wall are 2205, both because of corrosion resistance, because this is exposed with coastal and de-icing salts, and because of its strength. Otherwise, much larger sections would have been needed, which would have been detrimental to the design intent. Since we do get questions about this, and this is sustainability related, I did want to point out that stainless steel is 100% recyclable into new stainless steel with no loss of properties. We have an average service life of 20 years, but there's certainly many projects, including the Chrysler Building, which document that you can achieve 100 years of design life without problem if you've specified the right stainless steel. I also wanted to point out that we have, as an industry, tracked the carbon footprint of stainless steel. And between 2015 and 2019, that carbon footprint has declined. There are some critical factors that are needed to continue to reduce the carbon footprint of stainless steel, including the accessibility of alternative energy sources for running the plants, designing for longevity, and reducing material replacement is critical as well. I mean, there are too many materials that are replaced on buildings don't really have to be. We'd also like to increase the scrap that's available for recycling, and a lot of that has to do with design. Please, if you are designing a project, make it possible to separate the materials at the end of life, so that they can be reused. Now for some examples of sunscreens. It seemed important to talk about the passive versus what are considered the high performance operable shading systems. All shading systems will provide glare-free daylight if it's, if designed properly, and reduce the thermal impacts on building and enhance, of course, occupant health and comfort, and reduce demands on the utility. The benefit of the operable shading systems is that you have control. You can, bring in more light and in the colder months and let the sun help heat the building. There's greater control over bringing in fresh air and making and other adjustments that can help to optimize the shading system. And I should note, just as a historical note, that the first operable computer-controlled uh, sunscreen was built about 40 years ago. We've come a long way since then. I know that that particular project, which was in upstate New York in the United States, uh, eventually ran into problems in terms of maintenance. But we've come a long way with what's available and um, and the control systems. Here's an example of passive sunscreens on a university, Cooper Union in New York City. These are perforated stainless steel sunscreens attached to a structural frame. Gates Hall at Cornell University, you can see more perforated sunscreens and the frame to which they are attached. Um, another image of the same building. It did uh, reduce the energy use by 30%. I should note that this was modeled using ComFen. They worked directly with Lawrence Berkeley National Lab to do this. An example in China of another um, sunscreen that is passive, stainless steel wire mesh in this case. And the high rise in Abu Dhabi, Capitol Gate Tower, which got uh, quite a bit of coverage when it was first completed. It was the first tall building to have sun screening like this. So it was a breakthrough at the time. And the modeling, again, using ComFen, predicted that they could achieve a 30% drop in heat gain by using those sunshades. There are many other examples of passive sunscreens around the world. I'm sure you've seen some out of multiple materials. I'm obviously focusing on stainless steel. Here's an example in Spain, again with woven stainless steel. Here is a variation on an operable sunscreen. In this case, it's manual. This is a university building which had a large glass wall with operable windows that faced southward. No air conditioning. And the university decided because it was too hot in this building to be comfortable using it in the summer months, that they had to add air conditioning or make other changes. And the architect did an assessment and determined that if they just added sunscreens, including keeping the windows operable and making it possible to open them, as shown here, that they could avoid adding air conditioning. Uh, the ThyssenKrupp campus has numerous buildings on it. This is one. It was an experiment in all that could be done with sunscreens when it was completed. And here you can see a louvered system on one of the buildings. And one side of the louver has a reflective finish, the other dull. They can move the louvers so that they increase the level of light coming into the building or decrease it. Open the louvers to let in more light. Of course, move them sideways, as you can see midway up the picture. So they have tremendous control over these louvers and what they can do, as well as, of course, the air handling system. So they can let in more fresh air. It's an example of how sophisticated you can be if you have maintenance of your system. Now let's talk about some simpler sunscreens. If you don't want to dramatically change the appearance of your building, but you want sunscreening, one very um, popular concept is to use roller shades. Not on the inside, because shading on the inside of a window, while helpful, is far less effective than shading on the outside of the window. And here is an example on a building in California, and um, you can you can change um, how much shading occurs and when, based on the time of year and time of day. Here are a few more projects that used exactly the same type of exterior shading. So this could be added on to a building or part of new construction without making a significant difference in the visual appearance. Vegetated sunscreens are less popular in the United States than they are in Europe or other parts of the world, but they are an interesting concept um, that should be considered. When Australia built a new some government buildings, and this one, in particular, Council House 2, they wanted to make it as sustainable as possible. On the north facing, the hotter side of the building, they used stainless steel, an operable stainless steel wood slat screening system that you can see on the right. That's supported by type 316 stainless steel, and they can open and close those slats to shelter windows or let the sun in as needed. On the sides of balconies, on the north-facing sides of balconies, the hotter sides, they are encouraged vegetation growth to help shelter them. And then, of course, the overhangs on the balconies help shelter the inside too. So it creates a cooler envelope of air just outside um, the doors. They also did some research and found that if once a vegetated screen is grown over a roof, that the benefits are essentially equivalent to a vegetated roof in terms of reducing heat gain to the roof area. The plants hadn't grown in when this image was taken, but this allows them to use that roof space for different activities and helps cool the building. There are many different examples of what can be done with vegetated screens. Um, on the top left, a screen that was built around a building complex, both to shield it, increase privacy and security, but also to help cool the buildings. The top right is a university dormitory building. And rather than having railings, um, they have stainless steel woven mesh going, loosely woven mesh going up the side of the building. Plants are growing on it. So in the warmer months, walking, all up between rooms, you're in a plant shaded hallway essentially. And in the colder months, the leaves drop from the vines and they can take advantage of natural heating from the sun. I did want to throw in vegetated roofs because um, if you are designing a long-lasting roof and it will be vegetated, um, type 316 stainless steel is really the way to go. These are usually welded um, roofs. I mean, this is a particularly fancy one because it is a Renzo piano project building, uh, but it could be a flatter roof as well. Soil is very corrosive, making stainless steel, particularly a molybdenum-containing stainless steel, the ideal choice, so you don't have corrosion. There have been roofs lined by other materials like aluminum that have perforated because of soil corrosion. This is much more sustainable solution than using planters. And here is another example of a flat roof um, with the different levels of membranes. You can't assume that a liner, plastic liner, will remain in place over time. So let's talk a little bit about other aspects of design, specifically the durability of the materials. You have to consider that anyone inside a building will be looking out through those windows and seeing structural sections and the back of the sun shading system. And while the exterior might get rain washed, it's unusual for those structural sections or the backs of the panels to get any rain washing or manual washing. If you use painted metal, it will eventually fail. Um, I'm sure I'm not the only person who's looked out a hotel window or office building window and seen sunshades that are corroding like this. We're also going to talk a bit about avoiding galvanic and crevice corrosion because these designs are usually full of crevices, and unfortunately, sometimes galvanic corrosion has occurred. So, for any material, you have to look at the environment. Is there pollution? Is there salt of any type? In the building side will automatically be a shaded situation that won't benefit from natural rain cleaning. Or at most, maybe rain can come down between the gap between the shade and the building, but that's simply not the same level of washing as what you have on the exterior. So you have to consider if there will be any maintenance um, of that. Will they clean? Are they willing to clean the back of the panel and the structural sections as they clean windows? I've never seen it happen, but perhaps it would on some buildings. Crevices have to be considered. You're bolting things together. You have metals or materials that are probably expanding and contracting. So if you have tight unsealed joints, it is possible you could have crevice corrosion there. The other common issue is using combinations of materials that might originally have been separated, perhaps by paint that's going to disappear pretty quickly, or by something, an inert washer. But you have to consider whether it will last over time because these are large structures that are going to be moving throughout the day. Finish does make a difference. The smoother the finish, the less what is corrosive in the environment will be retained on that surface. A smoother finish also retains moisture for a shorter period of time. All of this is important as you do an assessment. This is a U.S. total salt deposition map. 60% of the U.S. population lives in coastal areas. And I should note, that's true globally. Um, whether we're your project is in the United States or another part of the world, you're going to see the kinds of variations in how far inland salt is carried as occurs on the US coast, where it can simply be a few miles inland to many, much further than that, at high levels. But globally, 60% of the world's population is coastal. So if salt is present, that has to be considered. If you live in a part of the world or have a project in the part of the world with de-icing salts, those salts are not limited to the highways. This particular study that was done jointly by the Illinois State Department of Transportation, the U.S. National Atmospheric Deposition Program, and Argonne National Lab documented that dry salt particles were found as much as 1.2 miles from roadways. I personally documented them up to 2 miles from a roadway. And they found that they go quite high on buildings. The highest I have ever seen it on a building was in Chicago, which uses a lot of de-icing salts. It has a lot of wind. And there it was up to the 59th floor of a building, and stays in the air for days. The highest concentrations are closer to the roadways, but some of the salts that are increasingly being used, like calcium and magnesium chloride, seem to be lighter particles that are carried further. So I mentioned salts. All of these salts are found in coastal salt, although sodium chloride is the dominant salt. We used to just de-ice with sodium chloride. Calcium chloride and magnesium chloride are increasingly used for de-icing. When we used to just use sodium chloride, winter rain, spring rain and early summer rain had a chance to wash away a lot of those salts before we hit 10 degrees C or 50 degrees Fahrenheit and 76% humidity. These are the critical temperature and humidity combinations at which these salts start to pull moisture from the air and create corrosive salt slurries on the surface. With the calcium and magnesium chloride that are increasingly being used for de-icing, as soon as the surface is above freezing and there's at least 45 to 50% humidity in the air, they are actively pulling moisture to these salts hygroscopically and creating a salt slurry. So our environment is changing and it's become much more corrosive. So I've mentioned several different stainless steels. This is color coded by corrosion resistance level. The pitting resistance equivalent number is meant as general guidance so that you know the relative corrosion resistance of different stainless steels. There can be specific applications where what's most appropriate changes. But this does give you a feel for relative corrosion resistance. So the least corrosion resistant stainless steel I've discussed were the precipitation hardening like 17.4 pH. 304 is a step up. 316 is a step up, and there's a duplex 2304 that's around the same level of corrosion resistance. There are other proprietary duplexes that are in that general range as well. Another big step up is 2205, which is very commonly used globally. 2205 has been used to support sunscreens in more corrosive locations. I showed you an example with the building in Boston that Maya Lin designed with the stone sunscreen. The image I've showed at the Stockholm Congress Center is another. That's 2205. So that would be your typical step up if you need more corrosion resistance or if you're really concerned about chloride stress corrosion cracking. Um, 2507 could potentially be used as well in a very severe environment. So when we talk about different stainless steels, I think it's helpful to just see the difference in corrosion, right? These are all pictures from Pittsburgh, Pennsylvania, where I live, where the salt exposure is de-icing. All of these images were taken about 3 years after the last time the buildings had been cleaned. The 430 building has the highest level of corrosion staining. If you wipe that off, there is visible pitting. The 304 is pretty superficial corrosion, but it's certainly not aesthetically acceptable. And then 316 just has some bird droppings. And you can see a little bit of the white powder along the bottom edge. So, I mean, that's the difference that alloy choice makes. As you look at a sheltered environment, there is a wealth of research around the world that's been done comparing sheltered locations to those that are not sheltered. One of the most extensive studies was done in Japan, where they looked at a wide range of buildings and put samples in sheltered areas under the eaves versus on the roofs, different distances from the coast, and then publish that data rather than a one location specific uh, data point. And if you look, you can see that the samples on top of the roofs that were rain washed didn't have a lot of chloride accumulation. Well, the more sheltered the location was under the eave, which is essentially what you have with the area behind the sunscreen, the higher the salt accumulation. Um, and for that reason, you really need something that is more corrosion resistant um, behind that for the back of the sunscreen or the structural supports for it. We have corrosion data from around the world. I threw in one from Dubai just to illustrate that we do have corrosion data from around the world. This was specifically a standing seam roof example where you can see the significant difference in corrosion rates between different metals. It is critical to pick an appropriate metal for a location. Uh, this is an example of another 2205 sunscreen in Saudi Arabia, quite close to the coast. It's the King Abdulaziz Center for World Culture. This is 2205 tube, some of it compressed to allow light through windows that was used for shading. This is not going to be cleaned. The previous the study that I showed you on the previous slide was made available to the designers so that they understood if they used 316 in this location, they'd probably have corrosion staining pretty quickly. So they used 2205 to make sure that the building maintains the design intent. It's critical to consider galvanic corrosion. I have been present in numerous meetings where at architecture firms where the principal responsible for specification stopped the presentation and said, "Everybody pay close attention. We are not building another building that's going to fail by galvanic corrosion." And these were typically, it could be curtain wall. Sunscreens are a particular issue because whatever is corrosive in the environment will settle on surfaces behind sunscreen. So I've seen examples where stainless steel panels were supported by aluminum, and the aluminum because of the if you know it corroded to protect the stainless steel. And so the structural sections were failing quickly. Same thing could happen if it was carbon steel. Um, as parts move, as I'm showing in this image, any paint system is going to fail. This is stainless steel connected to painted aluminum, and you can see a lot of aluminum corrosion product around that interface where the paint has been lost. You have to consider the moving parts and whether whatever your separation system is will last over time. It's much better to have it all be stainless steel. We have a lot more information on this topic in some of the brochures that I will mention to you at the end. But if you look at this, you can see I marked 304 and 316 in gold. Everything else is in black. Um, anything to the right of those, that 304 and 316, will corrode to protect the stainless steel. You can see where aluminum is on the scale, mild steel. Stainless steel and copper alloys can often be used together. Stainless steel is often used as structural supports. Um, so it really depends on the design, but you do have to consider galvanic corrosion. And then you also need to determine how you can protect it long term. So the image is of type 316 structural sections that were holding a private residence about the equivalent of about 2 floors off the ground because it was an area where coastal storm surges, were a potential problem. They used galvanized steel bolts to hold this in place. So this whole structure was at risk because of the bolt choice. Um, these should have been stainless steel bolts. So when you have dissimilar metals, they are in direct contact and moisture will be present to connect the metals on a regular basis. You have a potential issue. You have to consider the relative surface area of each. So inert washers or similar are probably your best option if you can't use entirely the same material. Crevice corrosion, it is a big consideration in many sunscreen designs. Whether we're talking about bolting together components or something that a sunscreen that is woven or otherwise has tightly overlapping pieces of metal. The bolt that I'm showing in this image uh, was on a pavilion on the Florida coast. The only corrosion was at the under the fasteners. There was nothing to seal that crevice. Um, the advice I ended up giving to them was to, gradually individually remove the bolts, clean behind everything behind them, use a little clear sealant, and then tighten them down because that they couldn't use a an inert washer because of structural requirements. But they were able to use sealant like that without it being a problem, and it did solve the problem. But wherever you have a tight gap that moisture and salts or other pollutants can enter, but where you don't have freely circulating air, you have the potential risk of crevice corrosion. The duplex stainless steels are much more resistant to it, which is another consideration if you need the higher strength of duplexes as well. These are some examples of where you might have crevice corrosion. Woven stainless steel between the wires, that's crevice corrosion. But you can get woven stainless steel. First of all, doesn't have to be a rope, which is having the bigger issue in this picture. But you can also get it in higher alloys. Um, if you have perforated holes and they are not cleanly cut, there's overlapping metal, and that's what's causing the corrosion in the other picture. So I've mentioned quite a few things. I do encourage you to, if you don't already have it, to download the over 550 PDF library that the Nickel Institute and AMOA assembled. It's available on AMOA's website. It gives you a full library of stainless steel. Unfortunately, we're getting part of the bottom cut off, but the Nickel Institute has a technical help line. Please go to their website and ask for assistance. They will put you in touch with the appropriate people. AMOA has a stainless steel selection system that can help guide you, and then specific pages on issues like coastal salt and de-icing salt and soil corrosion. The Nickel Institute has guidelines for corrosion prevention, which talks about many practical aspects of atmospheric corrosion and data. It also has a lot of other brochures on specific environments, should you need those. There's also stainless steel producer published guidance. The National Atmospheric Deposition Program and maps are very helpful in the United States for determining if you're in a coastal zone. And there's, of course, corrosion research that can be accessed by an expert in the field. So stainless steel sunscreens can give you longevity, including in severe environments. It's capable of the long life that you need with low maintenance and is a highly recycled and high recycled content material. Sunscreens as a whole can dramatically reduce energy use. And whether they are motorized or passive, the choice is really driven by how much maintenance is likely to occur and other factors, but we do encourage you to consider delving into this topic. We do have information, particularly on AMOA's website, different brochures delving further into this topic and some articles. I'm happy to answer any questions that you might have.
If you have any questions, feel free to type them into the Q&A, or if you're joining us from LinkedIn Live, just post them as a comment in the chat and we'll read them out for Catherine to answer. We'll give people a few minutes to ask questions, but yeah, thank you.
I'm not seeing any so far. Are there any on the live side?
No, there aren't any questions over there. Now, there is a little bit of a delay for the live stream, so there may be a few in a few minutes, but at the moment there are not any questions.
Well, I do, while we're waiting for questions, if there are any, I do hope this was helpful for everyone and encourage you to take a look at some of the resources we shared. they should be a big help as you consider using sunscreens on your buildings, and of course structural stainless steel.
Thank you, Catherine. Still not seeing any questions on either side. If anyone has a question, please feel free to ask it. We'll still hang out for a little bit here. Okay, there still aren't any questions on LinkedIn Live. Thank you everyone for joining. Catherine, do you want to conclude or?
Well, I don't have any other remarks other than I do hope that this was helpful, and this was recorded, so I believe it will be posted. And do please check out some of the resources that I've mentioned. I think they'll be a big help to you.
Okay, and with that, we're gonna close down the webinar. It will remain as a live recording on LinkedIn Live. If you are wanting a individual link of the recording, please feel free to send us an email, and we will get that over to you. Thank you so much and have a wonderful day.